Well, we've learned about derivatives and some different ways to take derivatives and different rules. And now we get to do a lot of application with derivatives. That's what a lot of this chapter is about. So we're going to start off with something called related rates, which is kind of like doing word problems with derivatives. And we're going to make quite a bit of use, and I think it's best to make use of implicit differentiation when doing this. So hopefully you master those skills really well. So our learning objectives are to express changing quantities in terms of derivatives, find relationships among derivatives in a given problem, and use the chain rule to find the rate of change of one quantity that depends on the rate of change of another quantity or other quantities. Okay. So let's read this part here. Setting this up in many real-world applications, related quantities are changing with respect to time. For example, if we consider a balloon example, again, we're going to see a balloon example. We can say the rate of change of the volume V is related to the rate of change of the radius R. In this case, we can say that dV dt, the rate of change of velocity with respect to time, and dr dt, the related change of radius with respect to time. They are related rates because volume is related to radius. Okay, so here's a problem. A spherical balloon is being filled with air at the constant rate of 2 cubic centimeters per second. How fast is the radius increasing when the radius is 3 centimeters? So we can start off by looking at the volume of a balloon, of a sphere. Volume is going to be 4/3 pi r cubed. So we can express volume as a function of radius. And I know for me it's always tempting to take and solve for radius, but we're going to leave it like this and just realize that this 2 centimeters, that 2 cubic centimeters per second, that's our dV dt. So dV dt, I'm out of the writing window, dV dt equals 2 cubic centimeters per second. So when I'm going to move this over here a little bit, but when we do this, we're going to take the derivative of both sides. We're going to take the derivative with respect to t of the v equals the derivative with respect to t of 4/3, oops, that's not where the 3 goes, 4/3 pi r cubed. And on the left side, that's pretty straightforward. That's our dV dt like this, and that's going to be that 2 equals, and then on the right side, the 4/3 is a constant, pi is a constant, so we're going to have 4/3 times pi times the derivative of r cubed is 3r squared times dr dt. And our goal for this is to find the dr dt. This is what we're after here. We want to make it say dr dt equals. So everything else we actually have a value to substitute in for those. So the dV dt we said was 2. Then we have, oh, check this out. This is nice. This 3 can divide out with that 3. And we end up with 4 pi r squared. So it's 4 times pi times, and it said the radius was 3 centimeters, times 3 squared times dr dt. So again, the goal is to solve for dr dt. So we have 2 equals, it's 4 times 9, so 36 pi dr dt. So it's going to be 2 over 36 pi equals dr dt, the change of radius with respect to time. And that would reduce to be dr dt equals 1 over 18 pi. And this is in centimeters, so centimeters per second. And that's it. It's kind of fun. Okay, let's look at another one. What is the instantaneous rate of change of the radius in that previous problem when r equals 6 centimeters? So what do we have? We had our dr dt was equal to essentially, I can go back up to it, but it was, we had 1 over, well, it was really a 2 over, then it was a 4 pi times the r at whatever this is at this point. In this term, and this time it's 6. So it's going to be the 2 and the 4 reduced, makes it a 1 and a 2. So it's 1 over 2 pi times 36, because that's 6 squared. So it was 1 over 72 pi centimeters per second. So that's building off the last problem. Okay, let's continue on. This next one, it didn't come through when I printed it, so I'll just try to fill this in here. And it says, find the rate of change of total profit. So rate of change of profit. When you look in your book, you'll see one like this. And it says where, or with respect to time, where r of x, the revenue function, is 3x, and the cost function, c of x, is equal to 0.04x squared plus 0.3x plus 20. When x equals 14 and dx dt equals 27. So as you might have guessed, profit, P of x, is going to be R of x minus C of x. So the revenue minus the costs. So it's 3x minus the quantity 0.04x squared plus 0.3x plus 20. So that's going to be 3x, let's see. I have a 3x minus a 0.3x, so let me just go through. That's going to be negative 0.04x squared. I'll do descending order. 3x minus 0.3x is plus 2.7x. And then distribute that negative minus 20. So that's our P of x. So if I'm going to take the derivative, dp dx, the change of profit with respect to time, is going to be equal to, clean that up a little bit, P of x equals, is going to be equal to negative 0.04 times 2x plus 2.7. Oh, I forgot my dx dt plus 2.7 times 1, because the derivative of x is 1, times dx dt. So now we have the pieces we could put in here. We have our x, we have our dx dt, and we can substitute these values in. So what do we have? That's going to be, and by the way, negative 0.04 times 2 is negative 0.08. So negative 0.08 times, and the x is 14, times the 27, plus 2.7 times 1 times, and that's a 27 there as well. So what do we get out of this? We get $42.66 a day. And that's it for that problem. Now let's look at problem with airplanes. Here's problem solving strategies, solving related rates problems. Okay, assign symbols to all variables involved in the problem. Draw a figure if applicable, which we're going to do in the next one. State in terms of the variables the information that is given and the rate to be determined. Find an equation relating to the variables introduced in step 1. Use the chain rule to differentiate both sides of the equation found in step 3 with respect to the independent variable. This new equation will relate the derivatives. Substitute all known values into the equation from step 4, then solve the unknown rate of change. Okay. So here's the airplane problem. An airplane is flying overhead at a constant elevation of 4,000 feet. A man is viewing the plane from a position of 3,000 feet from the base of the tower. The airplane is flying horizontally away from the man. If the plane is flying at a rate of 600 feet per second, at what rate is the distance between the man and the plane increasing when the plane passes over the radio tower? Okay, so let me draw a picture here. So it's 4,000 feet up. This is 3,000 feet out. And I'm going to call this h for the hypotenuse. Now, if I relate the sides, x squared plus y squared equals h squared. Now, what we do know, we know x is going to be a constant. Y is the part that, no, y is a constant. X is changing because it's flying away. The airplane is going away. Okay. It's going that way, that direction there. And I'm just going to say it's 600 feet per second. That's our dx dt. So dx dt equals 600 feet per second. We want to know at what rate it's going away from the guy here that's watching it fly. And so that's our hypotenuse, so the right triangle. So what we want is dh dt. And you could have called that C, you could have called that Z, I really don't care, but that's the one that we're after. Okay, so if we look at that equation, x squared plus y squared equals h squared, and we take the derivative of everything, h squared there. Now, the constant here is the y squared, or the y is constant, so that's just going to be 0. So we end up with 2x times dx dt plus 2y times dy dt equals 2h times dh dt. Now, this middle term here, that change of our elevation, that's just going to be 0. So this term is 0. So what we're left with is a 2x dx dt equals 2h dh dt. And the dh dt is what we're after. So if I divide both sides by 2h, I have dh dt is going to be x over h times dx dt. So now we need to fill in the pieces here. Our dh dt is what we're after, equals x. Well, at the time this happens, it's 3,000 over an h, because it's the right triangle. And I don't know if you know about Pythagorean triples, but by the Pythagorean theorem, h would be 5,000. So it's going to be 3,000 over 5,000 times that 600. dx dt is 600 feet per second. So our dH dt would come out to be, ready for this, drum roll, 360 feet per second. So I want to stress that I don't think this is that bad once you see how these formulas, you can put them together, take the derivative by implicit differentiation, it starts coming together. Okay, so I'm going to go on to the next one. It's related to this problem. And it says, in this case, what's the speed of the plane if the distance between the person and the plane is increasing at the rate of 300 feet per second? So what we had was the formula dH dt equals x over h times dx dt. So in this case, we're given dH dt and we have to find dx dt. So that means we're going to have 300 feet per second equals x over h, and that was 3,000 over 5,000 times dx dt. And so if we multiply by the reciprocal, 300 times 5,000 over 3,000 is equal to our dx dt. So dx dt would be what? Uh, 500 feet per second. And that's it. Okay, moving on here. What rate of change is necessary for the elevation angle of the camera if the camera is placed on the ground at a distance of 400 feet from the launch pad and the velocity of the rocket is... So, drew the little triangle here. The camera is placed at a distance of 4,000 feet from the launch pad, and so our rocket is climbing at 500 feet per second when it's at 2,000 feet off the ground. So that'll be our y value, 2,000 feet. And what we're looking at is the tangent of theta. We wonder what the angle, what is the angle changing? So what relates the angle to these other quantities is the tangent function. So tangent of theta is opposite over adjacent, or in this case, y over x. And so we have y over 4,000. The reason I didn't put the 2,000 in for y is because that's going to be variable. We'll now evaluate so that the horizontal part's fixed. The variable change is the height of the rocket. So we'll take the derivative of both sides, and then we'll plug it in for the particular instance. So if I take the derivative with respect to t of tangent theta equals the derivative with respect to t of y over 4,000. We would have the derivative of tangent, remember this is secant squared theta, times d theta dt equals 1 over 4,000. Excuse me, 1 over 4,000 times derivative of y is 1, so then just dy dt. Now what's interesting here is then we're trying to find our target is this d theta dt. This is what we're after. So we can divide both sides by secant squared theta. So we're going to have a d theta dt equals, let me just move this over, give myself some more space to work. Our d theta dt is going to be that 1 over 4,000 times, and we're told that the dy dt is 500 divided by, and secant squared. Now here's the key. This is why I found this value here, this 4472.136, because that's our hypotenuse. So that goes here, 4472.136. Because we're going to divide by whatever secant is, and just recall that secant of theta is going to be hypotenuse, which is a 4472.136 over adjacent, which is 4,000. So I'm going to divide by 4472.136 over 4,000, and this quantity is squared because it's the secant squared, which is the derivative of tangent. So what does this give us? This gives us that our d theta dt, the change of the angle with respect to time, is going to be, and I was really surprised by this answer, by the way, when I put it all in the calculator, it comes out to be 1 over 10 radians per second. That was pretty cool. Okay. We have another one here. Okay, now this one didn't print the other one earlier. So this one was talking about the volume of a cylinder. And the volume for a cylinder is pi r squared h, so it's the area of the base times the height, like a prism would be. And it says volume of a cylinder of height 8 and radius r, so in this case the volume is going to be pi times r squared times 8. So we want to find the change of volume with respect to time, considering the radius. So the radius, we don't know what it is, but let's say the radius can vary. So let's do a little cylinder here. Not a great cylinder. That should be like that. Okay. So there's your radius at the top, and here's the height of 8. So this isn't that hard of a problem. All we're supposed to do is find the formula for the volume, the change of volume with respect to time. So d dt of volume is pi, I'm going to say 8 pi times r squared. Oh, d dt of 8 pi r squared. So our dv, change of volume with respect to time, is going to be 8 pi times 2r times dr dt. So our dv dt would be 16 pi r times dr dt. And that's it. Now we have another problem like this, another kind of shape problem. This was a cylinder, and the next one's going to be a cone. So water is draining from the bottom of a cone-shaped funnel at a rate of 0.03 feet per second. So we have a cone. Water's going out. So our dV, change of volume with respect to time, is 0.03 cubic feet per second. Okay. And by the way, the volume of a cone is 1/3 pi r squared h. So it's basically 1/3 that of a cylinder. Okay. So it says the height of the funnel is 2 feet. And the radius is 1 foot. At what rate is the height of the water in the funnel changing when the height of the water is 1/2 foot? So what I want to do is try to, with this formula I have, that this volume equals 1/3 pi r squared h, I want to try to put that formula just in terms of h. So if I look back at my shape here, I have, like, if I look at a cross section or even like a cutout of it, here's my radius, and this is my height. so that the radius equals 1/2 the height. So remember that this is 1 and this was 2. So the radius is 1/2 the height. And that ratio stays all the way throughout. So our volume can be expressed as 1/3 pi times 1/2 the height squared, because that took the place of radius, times the height. So our volume is 1/3 pi times 1/8 h cubed, or the volume is 1/24 pi times h cubed. It'd be good if I could do math in my head. I just look at my notes. This should be a 4, not an 8. I'm thinking cubed. The h is cubed, but it's a 1/2 h squared. Okay, so this becomes a 1/12 there. Okay, so if I'm going to look at the dv dt, take the derivative of both sides. So the derivative with respect to time of the volume is the derivative with respect to time of 1/12 pi h cubed. So our dv dt equals, and 1/12 is a constant, pi is a constant, so it's going to be the 1/12 times, let's put pi over 12, times, and then derivative of h cubed is 3h squared dh dt. And now I can put the pieces in. I know my dv dt is a 0.03 equals pi over 12 times 3 times, and our h in this case, what did it say the height was? They want to know the height is 1/2, so 1/2 squared times dh dt. So our dh dt is going to be equal to 0.03, and then divided by, so you have pi over 12. I can simplify that a little bit. It makes that a 4. And then 2 squared is 4. 4 times 4 is 16. So I'm going to take that 0.03. Let me just do this in another step if you don't mind. That's a 0.03 equals pi over 16 times dh dt. So my 0.03 times 16 over pi is equal to dh dt, which is approximately, I should, by the way, say it's a negative 0.03 because it's draining. So it's negative 0.153 feet per second. Okay. So again, the idea is that we were able to relate these two variables. In this case, we can relate r and h to get that down to one variable on the left, on the right side, and then we have a variable on the left, variable on the right. We know that dv dt. We're trying to find dh dt, and we can use our algebra skills after that. Okay, moving on here. So kind of the same problem. What rate is the height of the water changing when the height of the water is at 1/4 of a foot? So we've done most of the work for this, thank goodness. So this would become negative 0.03 equals pi over 4, because it was pi over 12 times 3, and then that reduced, times the 1/4 squared dh dt. So negative 0.03 equals, so 1/4 squared is 1/16. 16 times 4 is 64. So pi over 64 dh dt. So that's going to be, well, So dH/dt is negative 0.03. Let's do this times 64 over pi. And that's going to be approximately negative 0.61 feet per second. Okay. I think we've come, is this our last problem for this section? Hopefully. Already at 30 minutes. Yep. Okay, so in this next one, again, the example didn't come through, but we're talking about relating pressure and volume with the formula PV to the 1.4 equals some constant C. So we want to know what the change of, we want dV dt, the change of volume with respect to time. We know P equals 85, V equals 490, and dP dt, the pressure is going down, so it's a negative 80 or negative 10 kilopascals per minute. So we have this formula. We can take the derivative with respect to time of PV to the 1.4 equals the derivative with respect to time of the constant C. But we all know the derivative of a constant is 0, so that's just 0 there. So you're thinking, what about the other side? Well, don't forget, we have the product rule. So we're going to look at dP dt times V to the 1.4 plus P times 1.4 V to the 0.4, because I subtracted 1 from the power, and then times dV dt equals 0. So let's see. My goal is the dV dt, so I can subtract dP dt V to the 1.4 plus, I'll just do that from both sides. So we have P, let's say 1.4 times P times V to the 0.4 times dV dt equals negative dP dt V to the 1.4. So we divide both sides by 1.4 P times V to the 0.4. I thought this was really interesting here, is this V to the 0.4 and the V to the 1.4 same base, so we can subtract the powers, and that's just a power of 1. Okay. Now, what do we have? Our dV dt is going to be equal to, we have negative dP dt, so negative of negative 10. Let me slide this over. Times our V, which was 490, divided by 1.4 times our P, which was 85. And from that we get 41.1765 centimeters cubed per minute. That's our change in volume. Okay. And that will do it for this section. Long section. Only video for this part of this section, so interesting. Okay, I hope this helps.